Before we get to talking too much about the gas laws and doing some practice rearranging the equations, I want us to do some simple math review. For most of you, this is very straightforward and simple, but for the 10–20% of you that maybe need a refresher in algebra, this is actually where I get all of the mistakes in gas law problems, is simply not doing algebra correctly. What do I mean by that? If we start out with this equation, A times B equals C times D. If I ask you to solve for C, what does C equal? Go ahead and stop the video and do it. This one's easiest. Okay, stop it, solve for C. So in order to solve for C, we divide both sides by D, which gives us, D's canceling, C equals A times B divided by D. Super easy, okay? But then what if we do something very similar? A over B equals C over D. If I ask you to first solve for C, that one's pretty easy as well. So go ahead and do that. Prove to yourself you can do it. Now in order to get C by itself, multiply both sides by D. Your D's cancel. C equals D times A over B. Most of the time, 100% of you guys get this correct. The problem comes where I ask you that same question, A over B equals C over D, and I ask you to solve for D. That's where the mistake comes in. So solve for D, see what you get. How do I do this? I want to get D on top. That's my first thing, my first one thing I want to do. So multiply both sides by D, makes my D's cancel, and now I still need to get D by itself. So multiply both sides by B over A. Multiply both sides by B over A. A's will cancel, B's will cancel, leaving me with D all by itself on this side. And now C times B over A is my final answer on that. Okay, make sure you know how to do it. Oftentimes I will see D being like, we'll divide by C, and you'll say A over CB equals D. No, that's 1 over D. Okay, so make sure you know how to do simple algebraic rearrangements before starting on any of these gas law problems. Problem number 1 states that we have 1 liter of a gas is at standard temperature and pressure. The gas is compressed to 473 milliliters. What is the new pressure of the gas if the temperature remains constant? We now need to identify our variables. So on this side, I'm going to identify my variables, and on this side, I'm going to do the math and explanation. So our first thing that we said was that we had 1 liter. Liters are volume. So V1 is at 1 liter. Then we said at STP. What is STP? STP is standard temperature and pressure. So remember, your temperatures are always going to be in Kelvin, and so standard temperature is 273.15 Kelvin. And then standard pressure is going to be 1 atmosphere. And I'll fix all my sig figs at the end of the problem. All right, so that's the beginning. This was how it started out. But then it said temperature and pressure. Temperature is going to be kept constant. So my T1 is the same as my T2. And then it said you're compressing it. So you're changing that volume from 1 liter to 473 milliliters. And I'm going to go ahead and convert that to liters. You all do know how to do that. Then the only thing left is finding out what's my new pressure. Because if temperature stays the same, as I'm compressing it, you can picture those gases, those little gas molecules flying around at 1 liter, and then as I'm compressing it down, what do I expect to have happened to my pressure? I'm expecting them to bounce around. Pressure is simply the force on the outside of whatever your container is. So as you start out with a big volume, lots of molecules floating around and hitting that wall, as I'm compressing it, think about it. They're going to hit each other more. They're going to hit the edges more because there's just a smaller volume. And so as you reduce your volume and you keep your temperature constant, you're going to increase your pressure. So we're wondering, what then is my new pressure? And common sense says it should be bigger than what it started out at, of 1.0 atmospheres. So what equation can I use? I could use my big combined gas law, P1 V1 over T1 equals P2 V2 over T2, but my temperatures are constant, so they're going to cancel each other out. It's like having the same thing on both sides of the equation. So really, I'm just going to use this equation here. Pressure times volume equals the new pressure times the new volume. And now I plug in my variables and solve. If you want to, you can first solve for P2. So divide that volume over here, and we get P2 equals pressure 1, volume 1 over volume 2. And now we plug in our variables and solve. So pressure 1 times volume 1 over volume 2, and that's going to give us our pressure 2. But notice our units need to cancel. So liters on top, liters on bottom. If you kept this in milliliters, that's fine, but this needs to be in milliliters as well. The only thing where that's not true for is temperature. Temperature must be in Kelvin. There is no other option or every answer will be wrong. Okay, you can't convert it at the end either. You have to do it at the step of the equation. So now you put this all in your calculator, and we get P2 equals 2.11 atmospheres. And notice that is greater than the initial pressure, so this makes sense. We have successfully solved our problem. Question number 2 states, how hot will the gas inside a 2.3 liter balloon have to get to expand to a volume of 4 liters? Assume that the initial temperature of the balloon is 25 degrees and the pressure and number of moles of the gas remain constant. So for this problem, we need to do the same thing. Identify our variables, solve the problem. So what variables do we know? We know our volume, which is 2.3 liters. We know our second volume, it expands to 4.00 liters. And we know our initial temperature, which was 25 degrees Celsius. And we're asked to find what is the new temperature, assuming everything else was kept constant. All right, so what do we do first? Let's figure out what law we use. So we could do the same thing where we use our combined gas law. And if we do this, and we kept everything else constant, what does that turn into? Our pressures go away, and we're left with V1 T1 equals V2 T2, or Charles' law. So if that's the case, let's solve for T2. So we get T2 by itself. We've got T2 equals V2, multiply by each sides by T1. So T1 is on top, divide both sides by V1. V1 is on the bottom, and now we've solved for T2. So with T2 now, do we just plug all these values in and put them into these equations? Hopefully you said, no, Dr. Hyde's trying to trick us. I'm not. It's just we can't use Celsius. You have to convert Celsius to Kelvin. So remember, in order to do that, you just add 273.15 to give us a total of 298.15 Kelvin. And now we can put each of our variable into the equation. So T2 equals V2, 4 liters, times T1, 298.15 Kelvin, over V1, which is 2.3 liters. Solve that and we get T2 equal to 520 Kelvin, correcting for our 2 sig figs here. You could also, if you wanted to, convert that down to 250 degrees Celsius. But either answer is correct. It just asks whether or not you're asked for the answer in Kelvin or in Celsius. But this is an example now of Charles' law. Question number 3 says, there exists 1.26 moles of a certain gas at a pressure of 1.2 atmospheres, a volume of 31 liters, and a temperature of 87 degrees Celsius. You can change the volume to 22 liters and keep all other variables constant except moles. If we do this, how many moles of gas do we now have? So in doing this problem, go ahead and stop the video, identify all of the variables, and then decide what equation you're going to use. So I have identified all of the variables here. Your moles is 1.26 moles, your pressure is 1.2 atmospheres, your volume is 31 liters, your temperature is 87 degrees Celsius, your volume is 22 liters, and your moles is what we're trying to find. Now, I would go through and I would say, okay, it said these two are constant, so I don't need to worry about them. Okay, what I need to worry about is this was my initial state, this was my initial volume, This is my second volume, and then this is my second number of moles, which I'm trying to find. So let's look at our combined gas law again. Normally we just have P1 V1 over T1 equals P2 V2 over T2. But remember, we also have our combined gas law, which states nRT. And if we solve and get R by itself over here, that's the same thing as doing PV over NT equals R, which means we could also write our combined gas law as PV over N1 and 2. Put the N down there with temperature. And if we do this and we keep our pressure and our temperature constant, we're left with our volumes and our moles, also known as Avogadro's law. So we've got V1 over N1 equals V2 over N2. That's why there's not a lot of equations to know. You just know this one equation, and you can turn it into the combined gas law, or you can turn it into Charles, Avogadro's, Boyle's. You can turn it into anything, okay? The names are just who named it, but the idea of variables and what's constant is what tells you how all of the different laws are related to each other. Okay, so now let's go and solve for this. We're solving for N2. So get N2 by itself. N2 equals V2 times N1 over V1. Plug in all of our variables. N2 equals V2, 22 liters, times N1, 1.26 moles, all over V1, 31 liters. Type that into your calculator, do some math, realize there's only 2 sig figs, and you should get 0.89 moles as your final answer. Question number 4. Synthetic diamonds can be manufactured at pressures of 6 times 10 to the 4th atmospheres. If we took 2 liters of gas at 1 atmosphere and compressed it to a pressure of 6 times 10 to the 4th atmospheres, what would the volume of that gas be? So go ahead and stop the video, identify the variables, and then go ahead and try and solve this one on your own before looking at my explanation. I hope that you use Boyle's law in order to solve this problem. And so pressure times volume equals new pressure times new volume. We're solving for volume, so we bring P2 to this side, and now we fill in our variables. And so in doing this, we have pressure 1, which is 1 atmosphere, times V1, which is 2 liters. Because remember, we're starting out at 1 liter and compressing it to 2 a new pressure of 6 times 10 to the 4th atmosphere. So we're starting out with 1 atmosphere and condensing that pressure, making it a whole lot more pressurized to 6 times 10 to the 4th atmospheres. Divide it now by that new pressure, and that will equal our new volume. So am I correct in that we condensed it to make it more pressurized? Absolutely. So new volume is going to be 3.33 times 10 to the negative 5 liters. And this is another example just using Boyle's law. Question number 5 is a little bit different. It asks you to do a little more thinking. An average pair of human lungs contains about 3.5 liters of air after inhalation and about 3 liters of air after exhalation. Assuming that the air in your lungs is 37 degrees Celsius and 1 atmosphere, determine the number of moles of air in a typical breath. All right, so what I want you to do here is think through the variables, try and figure out what's going on, and identify what you've got to start out with. So with this problem, it's not just the straight up, take your variables and plug it in. It requires you to use a little bit of thought, which we're a fan of. So in this case, if you're breathing in, so that's your inhalation, and you breathe in 3.5 liters, and then you breathe out 3 liters is now your new pressure inside of your lungs. So if your pressure when you breathe in is 3.5, and when you breathe out, it's 3 liters, which means how much did you breathe out? What was your typical breath volume? I hope you realize that if you just subtract them, you're going to get 0.5 liters, and that's that volume that you pushed out. So that's 3.5, now 3. And so those different changes in your lungs capacity is due to this 0.5 liter that you breathed out in a single breath. So that tells me my volume is 0.5 liters. So if I have one temperature, one pressure, and one volume, that should tell you that you should probably use the ideal gas law. PV equals nRT. But how do I know? That's the one question I get the most from students. How do I know what equation to use? I let the things that I've identified as my variables dictate my equation. Because in this case, I only had one of each variable. I don't have two. Sometimes this type of question is confusing because you're like, but I had two volumes. You didn't. You had things that created the one variable. All we cared about was the air that you breathed out. We didn't care about the total initial or final lung capacity. Those would be different types of questions. This one makes it so we only have one of each type of variable. Okay, is there any other variable we haven't defined yet that we need? I hope you realize we need R because we're trying to solve for N. But if we don't have R, we can't solve. But we know R. R is our gas constant. And that's liters times atmospheres per mole K. And what's really neat about the units for R is if you ever forget what the ideal gas law is, you can just use R's units to help you figure out what to solve. Let me get you there. Okay, well, when we check our units at the end, I'll kind of show you what I mean by that. So we're solving for N. So let's get N by itself. And let's plug in all of our variables. So N equals my pressure, 1 atmosphere, times my volume. These are really just like logic puzzles that help you get there. R, 0.0821 liters times atmospheres per mole Kelvin. And remember, there's lots of R constants that you could possibly use. For gas laws, you're always using this one. And that's also another reason why you got to make sure you always put your temperature in Kelvin. Because if you don't, your units aren't going to cancel. What do I mean by that? Kelvin is on bottom, Kelvin is on top. Kelvins go away. Liters is on bottom of this equation and on top here. So liters go away. Same thing for atmospheres. So you're left with 1 over mole. Which isn't that the same thing as saying mole, which is what we want our units to be? Absolutely. So we've checked our units and we're going to end up with moles, which is what we want our units to be. And now we can just type all this in our calculator and we end up with moles equal 0.2 moles. Checking for sig figs based off of our 0.5 liters. And that is how you would do an ideal gas law problem.